Like on this one, like everything's like very clear. Yeah, it's like very hot.
Guess we'll start out then.
Oh, that's fine.
We're ready to start? Yeah.
Where's the engineering one?
So a couple of announcements before we begin. Thanks for coming to Fall CTF. We have our challenge video out now. You can view the challenges and new solutions there also, I think. We also are going to participate in amateur CTF this weekend, I believe. Next weekend. Come, there'll be free feedback. So, hi, I'm Juniper. I'm a helper. Been at SIGPwny for like 3 years now, majoring in computer science, and I like ESA lines.
My name is Ryan. I'm a helper. I'm a freshman in computer science, and this picture was taken. Yeah, this was taken before I got into UIUC, so it's very, I don't know, foreshadowing. Here's the flag for this meeting.
Actually, you know, if you take 4.3, like it's true for the kernel, the code is the documentation. Sure.
Yeah, good. Okay. So let's take a look at these two functions. They're both in Python, which is easier to understand. One of them, the one on the left, is called Fibonacci. The one on the right, I refuse to pronounce. So they're both sort of the same algorithm in general. You can sort of see the general conflict, but which one's easier to understand? Which one would you rather, if you were programming at a company, which one would you rather see in your company's code? Which one would make you submit your 14-day resignation letter? I think the one on the left is better. Who thinks the one on the right is better? I knew it. So this is the sort of the theme. We're going to talk about the basics of reverse engineering, the motivation for why you want to do it, different types of analysis you can do, abstraction levels, like how much you want to go from machine code all the way up to, say, interpreted code, or like more simpler things like even control flow graphs or stuff like that. And
Sure. Oh yeah, and then afterwards, we're gonna go over a couple of examples for applying these techniques.
Yeah. So what is reverse engineering? So the reverse engineering is the reading other people's code from the things they provide you, like binaries, or maybe sometimes it's like Python source code or things like that. And the goal is to understand the code. And the code is sort of never wrong because it's actually what's being run. So it's the ultimate documentation, or as some people say on LinkedIn, that the code is the documentation. Not all code is easy to read or well documented, I'm sure. I'm sure some of you have experienced this before. And sometimes it's even obfuscated for other reasons. So there's two types of big analysis you do. You do static analysis, where it's sort of reading the code or taking the actual structure of the code and looking at it. And it's more simple if the code's simple or it's hard to run. Like, for example, there's some CTF challenges where you have to run like ARM assembly, so it's easier just to read it than to compile it. And then dynamic analysis is actually running the code and then inspecting the program state while it's running through like a debugger, through a virtual machine, something like that. And that's more helpful if the code is complex, or if the useful data gets loaded into memory or registers or other things that you can actually observe from a debugger. And they're not a dichotomy. You can't. It's not just use one or use the other. You can use them together. Like sometimes in dynamic analysis, while you're running it, you can disassemble what function you're looking at, or look at what function you're looking at in order to better understand the structure. And sometimes in static, you can run a debugger, or you can even run sometimes a simulator for some kinds of languages, which makes it easier to do some kinds of static analysis. So there's different like abstraction levels, I guess. So at high level, there's like Python and JavaScript. So those are scripting languages. You have to write them sort of in text format. They're easier to analyze. They're easier to reverse engineer. And then you get lower to C++, C, and then eventually that gets compiled down to assembly or machine code. Those are much harder to analyze because they're much closer to the behavior actually at the processor level, like what data is being loaded, stored, and then what operations are happening. And everything goes down to machine code. So Python, you'll be running it in an interpreter, which then runs the actual code on the machine code, same with Java. And then C and C++ are compiled ahead of time, and then into machine code, which is run on your computer. So techniques, so how do we reverse engineer? So static analysis, there's stuff like function rewriting, so you take a complex block of a function. And then you try to see what it's generally doing, like for loops, if statements, things like that, also function calls. So you want to simplify it in order to better understand it. And then you can find known algorithms or patterns. Like if you see a binary search, it's pretty obvious from the code, or if it's like a merge sort, there's things like that which are easier to see through the general structure. And then there's also decompilers like Ghidra or Binary Ninja, which convert abstraction from low-level programs, like assembly programs, or sometimes there's like decompilers for Java too. And they turn like assembly into more readable C or into Java and things like that. And then finally, deobfuscation is renaming the function variables with more descriptive names. And sometimes obfuscation changes the control flow of the program. So instead of an if statement, they'll turn it into something weird like a check and then an exception and then a try catch around that, which isn't very useful to read. But you can use heuristics because most obfuscators are pretty consistent with how they transform source into output. They just use patterns and convert them. So you can use the same patterns to go back from the obfuscated code to the deobfuscated code. So this is sort of what it might look like at a more, I guess, closer to the machine code level. So you have an array, which is the array of 0 times 10, and then I equals 9, and while I is greater than 0, we double the index and subtract once. Can we simplify this code? Is there anyone else? Yeah,
You like just hard code the
yeah, you can do that. Anyone else? So move on. So here you can actually see a for loop, like right here. This is a setup, and then this is the end, and then this is the condition. So if you look at, oops, is there something? Anyway, this is like if you had a for loop, it would be like for I equals 9, I greater than or equal to 0, I minus minus, or something like that, which is what we do. But you don't do that in Python. In Python, you would tend to implement that as a range. So for I range from 9 to 0 minus 1, because if you look at this in the last loop, iteration of the loop, I will be 0, and then it will go to -1 at the end, because this is the condition at the start, while for loops and the condition at the end. So then if we go to 9 to -1, going down by -1 every time, we have array of I equals I times 2, which is the actual body that we were looking at. Can we simplify it even more? Yeah.
you like instead of like having an array of zeros, you could like append, have a counter, and then you put your flow, then just append like the cards.
Yeah. Yeah. So that's the next. Oh, that's actually here on this slide. We have the for loop as a list comprehension, which is something that's quite familiar to Python developers. So for I range 0 to 10, we just create I times 2. So which level of simplification is most useful? But sometimes it depends. If you're analyzing something more complex, you might not want it to be simplified all the way down to here, because sometimes heuristics create a really poor something here, like it would put in 2 complex operations, set of I times 2 might be as several functions, that it's not easy to understand what's going on. So if you want to get the closest to the actual behavior, you can probably tend to look at the original code, and then anywhere in between is useful depending on what you're interested in, what you're trying to find out. So dynamic analysis is partial evaluation. You evaluate small portions of the code to reduce the complexity. You observe the behaviors such as variables. You can even modify programs, like a lot of reverse engineering tools have ways to modify different pieces of code, recompile it, and see how the behavior changes, or like add parts where you can examine what's going on. So you can add or remove code, you can add print statements, and yeah, I was just talking about. So you can go even further with debuggers like GDB and PDB, that's the Python debugger. And you can even use side channels, which is something we'll talk about later, like instruction counting, which is like how many instructions it takes, or time counting, like how long does it take to finish. Yeah.
So now I'll go over a couple of examples. So example, here we have some code asking what is the flag, and then does some computations, and then it says that's definitely wrong, or wrong flag, or it will continue. So if we want to get this to print correct output, or like pass this without saying that's wrong, what are some things that we could try with using modifying code?
Then you might want to separate out that like giant array expression there and some like simpler expressions even evaluate it by minute.
Yeah, that's a good idea. Any others?
Just print the array.
Yeah, we can also print the array. Any other ideas? Well, so yeah, both of those were good ideas. In the slide we have we just print the array, yep. And then if we run the code, then it will say flag. Here's another example for reverse evaluation. So let's say we want to pass this check, so we want it to print success. So we can see, so here we want W to be equals to this value. So what we can do is start assuming that W has the value 30, 91, 62, and we can go backwards. So what do we need to get W to be equal to 30, 91, 62? Yeah.
Is it like 396?
Yeah. And then what's next?
693.
Yep. And then what's next? And then 99. Yes, 99 up there. So then what's next? As a hint, word takes the ASCII value. So what character has ASCII value 99? What's it? Yeah. So yeah, if we have, even if we have like this messy bunch of functions and operations, we can take it step by step and go backwards through it, and then get a value of like what we're expecting. So that's all. Go try challenges. Go to ctf.sigpwny.com. I recommend starting from Python Re 1 if you want to do the challenges. And next meetings, we have x86 assembly this Sunday. And I believe we don't have a meeting this weekend.
We will have a meeting on Thursday. You just haven't put it up yet.
Oh, okay.
Yeah, it should be Rev 2 actually.
We'll have Rev 2 this Thursday, and we're doing amateur CPF this Friday. Here's the meeting flag. Thanks. Go solve challenges.
Please, I can let this. Hopefully it's